Okay, hi everybody. Let's get started with the first section of Chapter 10. This is section 10.1 on the topic of torque. And we have two examples here of torques. On the left, we have a torque wrench causing this bolt to turn. On the right, we have a cyclist pushing down on a pedal, causing the gears to turn. Right? So these are both examples of torque. When you have a net torque, you're going to cause something to rotate, or you're going to speed up its angular velocity or slow down its angular velocity. So any change in rotational motion is going to be the result of a net torque. And torque is going to turn out is going to be a vector. So part A of this lecture is going to be based on figuring out the magnitude of this vector. Okay, and part B is going to be based on calculating the direction of the torque vector. So let's get our brains working and just start with a clicker question. Here we're trying to turn this bolt. Maybe it's a stuck bolt. And we put a wrench on the bolt and we try to turn it, and we apply a force at point A in this direction and see what happens. Apply a force at point B in this direction and see what happens. Apply a force at point C here in this direction and see what happens. And they're all the same magnitude force. Say they're all 20 newtons. Which of these forces is most likely to cause that bolt to rotate? So pause the video, take a moment to think about it, and then I'll move on to the next slide right now. So the answer here is force B. Okay, force A is going to cause this bolt to rotate. We have a force applied at some distance. That means it's going to apply a torque, and it is going to cause some rotation. But since this force is applied relatively close to the axis of rotation, it's not going to be very effective for turning that bolt. Right? There's not very much leverage. Force B is applied at a much greater distance in effectively the same direction. And so force B is going to be more effective. There's more leverage for force B, and force B is going to be more likely to turn that bolt. Force C is also applied at a great distance from the bolt, but the direction is not very helpful. Right? This force is along the radial direction towards the axis of rotation, and that is not going to turn that bolt. Right? That force is going to be just pressing on the bolt and not causing it to rotate. So that force is not going to cause a torque. It is not going to be very useful for turning this bolt. Right, so that gives us a bit of a conceptual idea of how torque is going to work. So as I mentioned, changes in velocity are caused by a net force. So this is what we've seen before in Chapter 4, Chapter 5. What causes acceleration? What causes you to speed up or slow down? That is a force, right? But what about changes in angular velocity? Right? If I have a wheel that's initially not spinning and I want to start it spinning, how do I do that? Some forces are not going to be effective, like force C in the previous problem. Force C is not effective. So in order to cause angular velocity changes, right, to cause angular acceleration, what we need is a torque, right? And so that's the idea here. A little bit more about torque. We're going to define this precisely using a physics definition. It's going to be a vector, which means it has a magnitude and a direction. And it turns out there's going to be 3 different ways to calculate torque. They're all going to give you the same answer. They're all equivalent. I'm going to teach all 3 ways. You can choose which one works best for you. In some cases, one may work better than the other. There's going to be one that I really prefer, but I'm going to teach all 3. And in order to just better understand torque, let's make a few quick observations. Right, so first, and we've seen this already in the clicker question, it is easier to rotate something if you are far away from the axis of rotation. All right, so you can try this at home. Just open your door a little bit to your room, and just so the door is unlatched, and press really close to the axis of rotation, right? And that door is going to be really hard to open. Where if you press on the outer edge by the doorknob, it's going to be really easy to rotate. Okay, so the same force does not result in the same torque. Okay, so that's our first observation. The second observation, again, we made this observation with the clicker question, is that the angle of the applied force matters. Right? If I try to turn this torque wrench, this red force is not going to help. Right? I'm just pulling on my torque wrench. I'm not causing any rotation. Where this green arrow is going to cause rotation. All right? So the angle of the force matters. So that's going to be important for us in modeling torque. And I'll quickly switch to a simulation here just to observe this a little bit better. All right, so I again go back to these ladybugs on the turntable, and if I want to make this turntable turn, I need to apply a force at some distance, and I cause some angular acceleration, and I've sped up the rotation of this object. I could apply a force in the opposite direction, and I could slow it down and make it speed up in the other direction. All right, so what I'm doing there, by applying a force at some distance is applying a torque. Right? And as long as I apply that force, keep applying that torque, that object is going to speed up and speed up and speed up in its angular velocity. And then if I want to slow it down, I can press the brake and I can apply a force which causes the thing to stop rotating. I could have also, see, I can just keep applying forces in this direction, make it speed up. I can apply forces in the other direction and cause it to slow down in its rotation, eventually making it come to a stop and even switch directions. All right, now I'm starting to make it switch directions. So that's the idea here with torque, and we can play with this a little bit with this simulation. Let me make this a little bigger for you. So this allows me to apply a force in any direction. You can see that if I apply a force let me stop this, okay. Let me try to do this carefully. It's a little hard to do with the simulation. Apply a force straight up, I'm not causing any rotation. Or if I apply a force in this direction, I start to make this thing turn. Okay, so not every force is going to be useful for making something turn. This force is not useful, right? The green arrow here is the useful part of the force. That is tangential to the rotating object. That is the useful part of the force, which is going to make this thing turn. Okay, when I press on the brake, I'm applying this tangential force, which is causing this to have angular acceleration and stop. Okay, so the angle of the applied force matters. The location also matters, right? If I apply a force at the axis of rotation here, this thing doesn't start turning, right? If I apply it really close to the axis of rotation, it'll start turning, but it won't turn very fast, right? This is a small torque. If I apply the same force further away, I get a bigger torque. Okay, so the leverage here, how far you are away from the axis of rotation, matters. Okay, so moving back to our slides here. So let's talk about, now that we know these two main concepts related to torque, let's talk about 3 different ways to calculate the magnitude of the torque. What I'll call method 1 is called the tangential component of the force method is what I call it. This is my preferred method because this is much more conceptual. It makes sense to me. So again, we're going to try to turn this bolt by applying a force on this wrench, and I'm applying the force in this direction. So I'm able to reach into this wrench and push on it in this direction. And the path of the wrench is going to follow, hopefully, is this dashed line, right? The end of this wrench is going to follow this dashed line, and it's going to move in a circle, right? And the bolt is going to move in a circle too. So in order to calculate the torque based from this force, first I'm going to draw a position vector. I'm going to call that position vector R. It's going to originate at the axis of rotation, and it's going to end at the point where I'm applying the force. Right? So it's a position vector starting at the axis of rotation that points to where the force is applied. And the magnitude of this vector is just the distance. This is 12 centimeters between the axis of rotation and where I'm applying the force. So that's I'm going to call my R vector, that's the position vector. The next thing I'm going to do is draw a quick axis here, and I'm going to define, instead of an X and Y direction, I'm going to define a radial direction, meaning it's along the radius of the circle, right? So in this direction, it's towards the axis of rotation. That's my radial direction, and I'm going to draw a tangential direction, right? This line, dashed line, is a tangent to this circle, right? So that's why it's helpful to draw that circle in. It helps you draw in that tangential line there, right? Once I've done that, I can break up this force into components along these 2 axes, right? So I'm going to break it up into a radial component. So the red vector has some component along this axis, this radial axis, which is this green arrow, right? So this is my radial component of the force, and this red arrow of the force of my push has some component given by this orange arrow along the tangential direction, right? So as you can kind of see now, just looking at the green arrow and the orange arrow, the green arrow is not going to help this thing turn, right? The green arrow is pushing on that bolt. It is not going to cause rotation. So that component of this force is wasted, right? It's not useful for turning. It's only this tangential component of the force that is going to cause this wrench to rotate, right? So that tangential component is a useful part of the force. So when we're calculating torque, we always have to figure out what is the useful part of the force, what is the tangential component of that force. Once I know that, I can apply it to our first formula we're going to use for method 1, is that torque, which we're going to use a tau symbol. This is the Greek letter tau to denote torque. is given by r times the tangential component of the force. So I multiply r, the distance between the axis of rotation and the point where I'm applying the force, times the tangential component of the force. All right, so the bigger r is, the bigger the distance I'm applying this force, the bigger the torque, right? And then the bigger the tangential component of the force, the bigger the torque, right? And so once I have this is a pretty simple equation to calculate. The only tricky part is figuring out the tangential component of the force. So let's do a quick example. Let's just say it's a 50 Newton force and it's applied at an angle of 30 degrees as measured, as given in the diagram here. So we're measuring from this blue arrow. Okay. So first we have to calculate the tangential component of the force. So this is the tangential component of the force, and I can move this vector around, move it to over here, so it makes it easier for me to calculate what the magnitude of that component is. And I can see that this component is opposite my angle, so I can use sine. And so this tangential component of the force is 50 newtons, which is the magnitude of the hypotenuse here, multiplied by sine of 30 degrees, giving me a tangential component of 25 newtons. All right, so if I had applied the force in this direction, I would have had a 50 Newton force applied at that location, but I'm applying it as force at an angle, and I only have a useful part of my force of 25 newtons. Okay, so that's my tangential component of the force. Once I know that, all I have to do is use our torque formula. Torque is equal to r F tan. So r is just the distance between my axis of rotation where I'm applying the force, so that's 0.1 meters, multiplied by 25 newtons. So my torque is 2.5 Newton meters. All right, so that's a unit of torque. It's r, which is measured in meters, times force measured in newtons. So we call that a Newton meter. Okay, so that was our first method to calculate torque. The second method is called the lever arm method. Okay, it's a little bit different. You get the same result. So let's use a similar example. We're applying a force at this location on this wrench. To use the lever arm method, what we're going to do is we're going to draw first what's called the line of action. So we're just going to draw a line in both directions in kind of parallel to the force direction. So draw the line in this direction and in this direction. Okay, that's what we call the line of action. Next, we have to figure out where on this line is the line closest to our axis of rotation. So here's our big line, here's our axis of rotation. So the closest point on this line is right here. Right? If I was here, it'd be a further distance to the axis of rotation. If I'm down here, it's even farther away from the axis of rotation. So I want to find the closest point on this line to this axis of rotation. That point is right here, and it should be the point where I can draw a right angle, right, like this. Okay, once I have that closest point, I draw a line from that closest point to the axis of rotation. That's what I call my lever arm. Your book uses kind of a curly L for that symbol, and that's what we call a lever arm. Once we know that lever arm, torque is very easy to calculate. It's just force times that lever arm. Right? So if this lever arm is 5 centimeters, it's just our force times 5 centimeters, and that tells us the torque. And you can see that this lever arm is going to get bigger or smaller, not only based on where I'm applying the force, but based on the angle I'm applying the force. Right? If I had applied the force in this direction, the lever arm would be longer. Okay, and I'll give you an example of that in a moment. So by applying the force at some angle, I decreased the size of the lever arm, and therefore I decreased my torque. Okay, so let's give this a try with the same example. So we're going to again use a 50 Newton force, again at an angle of 30 degrees. So first I have to figure out this distance. What is the length of my lever arm? Okay, so I know this angle is 30 degrees. I know this distance is 0.1 meters. So I have a triangle. I can figure out this side, which is opposite that angle. Okay, so the length of this side is sine of 30 degrees is given by opposite over hypotenuse. Right, I have a right triangle here. This is the opposite side. That's my unknown. That's my curly L. This is my hypotenuse. I know this. Right, this is how far my axis of rotation is from where I'm applying the force. That's 0.1 meters. So I can solve for curly L, and I find that my lever arm is 0.05 meters. And now to calculate the torque, I just have to plug it in. 50 newtons times my lever arm gives me 2.5 Newton meters. All right, so you can see that we get the same answer as the previous problem. Okay, and just some more examples of drawing in lines of action and lever arms. All right, so here's one similar to the previous example. here's an example where the force is applied more in this direction. So I draw my line of action, this purple line like this. And now the closest point on this line to my axis of rotation is right here. So that defines my lever arm. Okay. And in this case, I'm applying my force in this direction. So this is my line of action. And now the closest point to my axis of rotation is right here. And so that is this distance. So you can see that this example has the largest lever arm. Right? Both of these have a smaller lever arm. So it's optimal for me to apply the force perpendicular to this axis here. In that case, I have the biggest lever arm and I get the most torque. Okay. This method is useful, especially when you have some kind of large extended body. So here's a nice example from the book where here's some kind of weird shaped object and we're rotating, say, about point A. Right? If I want to figure out, rotating about point O, I'm sorry about that, with this picture. So I could apply a force in this direction. If I want to figure out the torque from that, I can extend the line in both directions. That's my line of action. This is the place of closest approach. That's my lever arm. So I just multiplied that distance by that force, and that tells me the torque. Right? So it's not this distance using this method. It is drawing my line of action and then figuring out my lever arm. Right? Force 3 is not applying any torque. If I draw my line of action here, it passes through my rotation axis. So there's zero distance between my line of action and my rotation axis. My lever arm is 0, and therefore this applies no torque. I'm just pulling on my axis without causing any rotation. This force, this is my line of action, this is my lever arm, so I'm going to get this force times this distance is my torque. All right, and that's going to cause this object to rotate. The last method to calculate torque is also the method we're going to use to calculate the direction of this torque vector, and it is a cross product method. So in chapter 1, when we first learned about vectors, we defined the cross product, and now we get to use this mathematical tool. We're going to get to understand why do we define it in the first place. Okay, so torque is defined by R cross F. The cross product of our R vector, the vector that points from the axis of rotation to where our force is applied, crossed with our force vector, right, that force vector there. And we know how to calculate the magnitude of this R cross F, because we know from chapter 1 that the magnitude of A cross B is the magnitude of A times the magnitude of B times the sine of the angle between those two vectors. Right, so we can use this mathematical definition to also calculate torque. We have to be very careful here, though, because this angle is, again, the angle between the two vectors when they're drawn tail to tail. So let's be careful about that. So let's demonstrate that by using the same example. We're going to apply that 50 Newton force at an angle of 30 degrees at a distance of 0.1 meters. Right? And we want to calculate the magnitude of the torque, again, using this formula. Remember, this angle in this formula is the angle between the two vectors when the vectors are drawn tail to tail. So we have to do that. Let's draw these vectors tail to tail. This is the vector that's useful to us, right? So this is the vector we have to, this is the angle that we have to plug into this equation. It may not be the angle given to you in the problem. Okay, so if they told me in the problem that the angle between this axis of the wrench and the force was 30 degrees, I can figure out that this angle, when they're drawn tail to tail, is 150 degrees. So when I plug into this formula, I get 0.1 meters times 50 newtons times the sine of 150 degrees, and that gives me the same answer we've gotten a few times now, 2.5 Newton meters. Okay. And so this method is useful. I find it to be a little bit less conceptually useful, so I tend not to use it when solving problems. It is going to be how we figure out the direction of a torque vector. But just be careful with the angles they give you in the problem. Right? If they told you this was 50 degrees, what is useful for this formula is actually this angle, 130 degrees, when these vectors are drawn tail to tail. They also could have given you this angle, 40 degrees. So be careful with the angles they give you in the problem. That also holds for some of our previous examples. For example, earlier we did the tangential component of the force method where we had this angle of 30 degrees, and we were able to figure out this component of that force, the tangential component, using opposite. So we use sine, but they could have given us this angle instead. Right? If they had given us that angle, the 40-degree angle, we would have used a cosine instead of a sine. So you don't want to memorize sine or cosine when calculating torque. You want to think about what angles were given to you in the problem and use your trig to figure out if you should use cosine or sine. Okay, so just in summary, we now have three different equations to calculate torque. Force times the lever arm, or Rf sine phi, that is our cross product definition, or our force, our tangential component of the force, times R. Right? So in this example from the book, all three are shown. Right? If I have this force in this direction acting on this object, right, this force, I could draw my line of action. Here is my lever arm, so that distance times my force is the torque. I could also use this definition, but in this case I have to draw my forces tail to tail to figure out that angle. And with this definition, I have to figure out which component of this force is tangential. So here's my force. This is my radial component of the force. This is not useful. This is my tangential component of the force. This is useful, and so I can figure out that component using some trig, and I can use that example. I really prefer this method of tangential because it is more intuitive, it's more conceptual again, but choose which one you like. And just finally here, this is what is going to be on your equation sheet. So the magnitude of torque vector is given by these three different equations. Each is equivalent, and I define for you here what some of these symbols mean in case you forget. So in the next video, we'll learn about finding the direction of torque.